Okay, so in this video, we will determine whether the series diverges, converges conditionally, or converges absolutely. So, let's look at the initial series. We are summing negative 1 to the n times n over n squared plus 3 as n goes from 1 to infinity. These terms are positive. Negative 1 to the n will give us an alternation in sign, so we have an alternating series. So, we'll look at whether or not the positive part of our sequence satisfies the conditions of the alternating series test. Well, is Bn eventually decreasing? It's not obvious as n increases to infinity, so n is increasing, n squared plus 3 is increasing. So we have an increasing over an increasing function. The result is not obviously decreasing. So we will of course look at the derivative of the continuous analog, namely the function x over x squared plus 3. And if we can show that the derivative is negative when x is large enough, then the function will be eventually decreasing and will be good to go. So the quotient rule, derivative of x is 1 times x squared plus 3, so simply x squared plus 3, minus x times the derivative of x squared plus 3, which is 2x, so 2x times x minus 2x squared, over, of course, our denominator all squared. If we simplify, we'll be left with 3 minus x squared on the numerator, over x squared plus 3 all squared. Well, this is clearly always positive because of the square. And look at the numerator. What happens to the numerator as x becomes larger and larger and larger? Well, 3 minus x squared will approach negative infinity. So when x is large, our derivative is something that will be negative over positive, therefore is negative. So the derivative of this function is eventually negative, therefore the function is decreasing, therefore the corresponding sequence is also decreasing. So Bn is eventually decreasing. And the other property that Bn must satisfy that we have overlooked so far is that Bn must be positive, but this is clear as n goes from 1 to infinity. N over n squared plus 3 is positive, and we have to prove that as n tends to infinity, Bn shrinks to 0. Well, let's see. Bn is quite simply n over n squared plus 3. We have an infinity over infinity case, but don't use L'Hopital's rule here. We can do much simpler. We can multiply top and bottom by 1 over n squared. You could also do 1 over n over 1 over n. This would also work. And so what do we obtain? Well, n over n squared is 1 over n. N squared over n squared is 1 plus 3 over n squared. So as n tends to infinity, 1 over n shrinks to 0, 3 over n squared shrinks to 0, and we're left with 0 over 1, which is clearly 0. So Bn satisfies all the conditions of the alternating series test. It is positive, eventually decreasing, and converges to 0 as n tends to infinity. So the alternating series converges by the alternating series test. AST, alternating series test. Okay, so we have convergence. Now what about the series of the terms in absolute value? Well, as n over n squared plus 3 is always positive when n is positive, this term in absolute value, well, all that's going to happen is we'll lose a negative 1 to the n. This is plus or minus 1. In absolute value, this is 1. So we'll have a very nice simplification. The series of the terms in absolute value will end up being simply n over n squared plus 3. And now we're asking, does this series converge or diverge? Now we have a series of positive terms. Well, we have a simple rational function of n over n squared plus 3. And here forget our previous work, namely that we let Bn be the positive part of the alternating series. So we're starting from scratch here. So we're summing these terms, which I'll call an. And every time you are summing a rational function of n, this is the perfect setup for the limit comparison test. So we're asking, as we can always ignore the first few terms of our series, we are asking, when n is large, what is an roughly equal to? Well, an is roughly n over n squared. As clearly when n is large, n squared is way larger than 3. This is simply 1 over n, which is now our Bn in the context of the limit comparison test. So we're saying quite simply, when n is large, the terms we're summing are roughly 1 over n. So summing 1 over n will return a simple p-series, and as p is 1, the p-series will diverge. So we suspect this series to diverge as well. But we have to prove that our intuition is correct, that an is indeed roughly Bn. And if you recall, in the limit comparison test, to prove that you are indeed correct, you have to show that in the limit, an over Bn approaches a positive real number. So an is n over n squared plus 3. Now we divide by Bn, which is 1 over n, but if you divide by 1 over n, you multiply by n, but n times n is n squared. And then we have a simple limit where the dominant term on top and on the bottom is n squared, and so we multiply top and bottom by 1 over n squared. Multiplying out, we're left with 1 over 1 plus 3 over n squared. As n tends to infinity, 3 over n squared clearly shrinks to 0, and we're left with 1 over 1, which is 1. So, our intuition is that when n is very large, an over bn is roughly equal to 1, and so an is roughly bn, again when n is large. Therefore, if we are summing the terms an, this will be approximately summing the terms bn, but bn is quite simply 1 over n. And as we've said previously, this is now a simple p-series, where p is 1, which is less than or equal to 1. And a p-series only converges if p is strictly larger than 1. So this p-series diverges, but as we are summing positive terms, the only way it can diverge is by blowing up to positive infinity. Therefore, the original series is roughly on the same order of magnitude as this divergent p series which blows up, so the initial series also blows up. Therefore, it diverges by the limit comparison test. And of course, we write this as LCT. So what is our conclusion now? Well, we used the alternating series test to show that the initial series does converge, but we showed using the limit comparison test that if we look at the series of the terms in absolute value, then this series diverges. So when the series converges, but the series of the terms in absolute value diverges, we have what we call conditional convergence. And that is our conclusion. So the series converges, but only conditionally. And that's it.